Today we'll be looking at Chapter 20, Part A, over the immune system. And the immune system provides resistance to disease. It's made up of two parts called two intrinsic systems, the innate and the adaptive defense system. The innate defense system is nonspecific. The adaptive defense system is specific. The innate defense system includes both the first and second line of defense. The adaptive defense system includes the third line of defense. The adaptive defense system is specific because it attacks particular foreign substances. It is specific for a particular antigen, but it does take longer to react than the innate, hence it being called adaptive. It takes time to adapt. The innate defense system is going to act first. It includes both the body's physical barriers and the chemicals and cells in deeper tissues. The immune system is definitely a functional system rather than an organ system. We see that its cells reside in both the cardiovascular and lymphatic systems, and we can often find lymphocytes, macrophages, and other immune cells in tissues. The innate and adaptive defenses are also intertwined. There are certain chemicals and pathways, specifically one that involves complement, where we see some overlap between kind of the triggering of each of these defense systems. I definitely recommend Figure 20.1. Even though it is simplified, it's just an overview of the innate and adaptive defenses. It's definitely a good starting point. We see that the innate defenses are listed as including the first line of defense, the surface barriers, which are skin and mucous membranes, as well as the second line of defense are internal defenses, the ones in our deeper tissues, which include cells such as neutrophils and macrophages, which are phagocytes, the non-phagocytic natural killer cells, inflammation, which is a hallmark of the second line of defense, as well as chemicals such as antimicrobial proteins like defensin and mucin, and fever is also going to be something we associate with the second line of defense. Fever is actually caused by chemicals called pyrogens. The adaptive defenses include the third line of defense. Within that moniker, third line of defense, we include both the humoral and cellular arms of the adaptive defense system. Humoral immunity associated with B cells, whereas cellular immunity associated with T cells. Let's look closer at the innate defenses. The innate system uses the first and or second lines of defense in order to stop pathogens. Pathogens are anything that cause disease. So that first line of defense of the innate system is going to consist of the skin and the mucous membranes, and definitely the skin and mucous membranes are physical barriers, but we also have to take into account their secretions. A lot of the secretions from these surface barriers are going to be resistant to bacterial enzymes and toxins, or provide a weak acidic or basic component that inhibits bacterial growth. Both the integument, specifically the epidermis, and the mucosae that we call our surface barriers are going to have similar mechanical barriers, or mechanisms to the mechanical barriers. So more on that acid, we have an acid mantle specifically to the epidermis, which is just an acidity layer of the skin. We do also find some acidic secretions that end up being on our mucosae. And acidic secretions or acidity of the skin, both of these things would inhibit bacterial growth or microgrowth. There's also plenty of enzymes like lysosome. There's enzymes in respiratory mucus and lacrimal fluids, and these enzymes are able to break down and or inhibit or kill certain microbes. And we can't forget the acid that is inside the stomach. The acid inside the stomach is also able to break down many microorganisms. Other chemicals include mucin, a sticky mucus that lines the digestive and respiratory tract and traps microorganisms. Defensins, very aptly named antimicrobial peptides that inhibit microbial growth. And plenty of other chemicals, ones that have actually been mentioned in Anatomy and Physiology 1, such as the lipids in sebum and the dermacidin in sweat. Let's look at one particular organ system, for example, and how it utilizes chemicals of the first line of defense to protect itself. Not only protect itself, but to keep these pathogens from getting into deeper tissues. We'll look at the respiratory system, which has modifications to stop pathogens. It has mucus-coated hairs in the nose that trap inhaled particles before they get too far. We have cilia in the upper respiratory tract, so that's going to be structures like the larynx, which is your voice box, and your trachea, which is your windpipe. And so we're going to see that these cilia in that upper respiratory tract are not only able to trap, but then sweep the dust and bacteria-laden mucus that coats these cilia toward the mouth so we can swallow it. And then when it gets to the stomach, the acid in the stomach hopefully takes care of it. Plenty of these surface barriers work every day, but if they're breached by nicks or cuts, that does trigger an internal or second line of defense, and that's going to be cells and chemicals that protect deeper tissue. In Table 20.1, we're just looking at the first line of defense, the surface membrane barriers, their secretions, and as long as you have intact skin and intact mucous membranes, we would not need to use the second line of defense. But when microbes get past that first line of defense, that's when the second line of defense for the innate system will come into play. So different chemicals and parts of the second line of defense include phagocytes, natural killer cells, the inflammatory response, antimicrobial proteins, and fever. Phagocytes include cells such as neutrophils and macrophages. Macrophages are monocytes that have gone into tissue. Natural killer cells are non-phagocytic, but they have the same mechanism of action as cytotoxic T cells. They both use perforins and granzymes in order to directly kill infected cells. The inflammatory response we'll spend a lot of time on. Expect to see things like macrophages and mast cells, different white blood cells, and inflammatory chemicals to play a role here. And then antimicrobial proteins, these are similar to things like the defensins we saw with the first line of defense, but two types of antimicrobial proteins we're going to focus on for the second line of defense are interferons and complement proteins. And we'll also spend some time looking at fever. Many of our second line cells are going to be able to have a pattern recognition receptor. This pattern recognition receptor is generally a toll-like receptor, one of the most common. It plays a central role in triggering the immune response, and these pattern recognition receptors, like the TLRs, are able to recognize and bind tightly to structures on microbes. And when they do so, they disarm them before they can do harm, before the pathogens can do harm. Humans actually have 11 different TLRs, and each is able to recognize a particular class of attaching microbe. So this may seem like the second line of defense is getting a little specific, but this is still a general recognition. It's not one particular antigen, which is what we'll see for the adaptive specific defense system. Let's talk about phagocytes in more detail. We're going to talk about not only phagocytes and examples, but what is phagocytosis? Phagocytes are able to perform phagocytosis, which is the ingestion and digestion of foreign invaders. Phagocytes are generally white blood cells. Neutrophils are one type. Macrophages, which are derived from monocytes, are another type. Neutrophils are interesting because not only are they the most abundant phagocyte, but they usually are the first phagocyte to arrive at the site of infection. Because they're the first to arrive, they don't have a lot of support, but they do fight valiantly and they die fighting. Oftentimes you'll see dead neutrophils in pus. They become phagocytic when they're exposed to infectious material. Macrophages, they develop from monocytes, but they're really our chief phagocytic cell. They're our most robust phagocytic cell, and they're going to arrive after neutrophils. They're also able to phagocytose a microbe multiple times, whereas neutrophils, they can phagocytose a microbe and they die in that process. There are both free and fixed macrophages. Free macrophages can wander, whereas fixed macrophages, you may expect, are fixed at a particular organ or tissue. The stellate macrophages in the liver and the microglia, which are macrophages of the brain, are examples of fixed macrophages. Here is a macrophage. It's in purple, whereas the bacterium it's trying to ingest or phagocytose is in green. It's a rod-shaped bacterium. We get this picture via an electron micrograph or scanning electron micrograph, and it's artificially colored. Let's look at the process of phagocytosis. Step one is when the phagocyte, such as a macrophage, encounters a pathogen, but not just a pathogen, a particular carbohydrate signature on the cell surface of that pathogen. And a carbohydrate signature could just be a cell surface marker. Some microorganisms can even hide by covering up their cell surface markers made of carbohydrates by kind of encapsulating them or having a slime layer. Well, one thing that the body can do in order to recognize these hiding microbes is to opsonize that microbe. Opsonization is a coding process. And now it doesn't always work if a microbe's really good at evading the immune system, but opsonization occurs when the immune system uses things like antibodies or complement proteins. These things would be acting as opsonins or the coating protein, and we would use these opsonins to coat pathogens. Essentially, we would put little surface markers that our immune system could recognize as, hey, that's something we should destroy, and that would enhance phagocytosis. Said another way, opsonization is the coating of a microbe to make it easier to phagocytose. The coating essentially puts molecules that act as red flags to phagocytes, making them easier to recognize by things like macrophages or neutrophils. The next step in phagocytosis, after the recognition and adherence of the phagocyte, such as a macrophage, to the microbe, is that we would want to see cytoplasmic extensions called pseudopods start to bind to and engulf the particle, create a vesicle in which the microbe is encased. That vesicle would be called a phagosome. Phagosomes then generally fuse with a lysosome, which contains acidic enzymes. Those acidic enzymes are able to then break down and digest the microbe. Anything left over we get rid of via exocytosis. When the phagosome and the lysosome came together, that would be called a phagolysosome. And so here is that process in figure 20.2b. So the phagocyte adheres, and then we would see the phagocyte takes in the pathogen or takes in the cell debris. The phagosome, which is the vesicle formed after we take in the pathogen, is going to then fuse with the lysosome, and the acid hydrolase enzymes of the lysosome will be able to digest the pathogen. And anything left over is going to be exocytosed as residual waste or material. Phagocytosis is not always effective because some pathogens are not killed with those acidified lysosomal enzymes. An example would be tuberculosis bacteria. But luckily, we can get help from the helper T cells of the adaptive immune system in order to enhance the phagocytic nature of macrophages. If helper T cells trigger macrophages to produce a respiratory burst, we have kind of a second mechanism by which we can kill pathogens that were resistant to those lysosomal enzymes. Because the respiratory burst is where we release cell-killing free radicals that contain reactive oxidizing chemicals like hydrogen peroxide, and that would increase the pH and osmolarity of a phagolysosome, and that can disrupt not only DNA but other cellular components. Also, we see defensins, which are in neutrophils, able to help or increase or ensure phagocytosis is successful by piercing the membrane of the pathogens they ingest. Next, let's look at natural killer cells. Natural killer cells are non-phagocytic, but they're really large granular lymphocytes that police the blood and lymph. You should know that natural killer cells can kill cancer and virus-infected cells. Now, people do develop cancer, and they do develop viral infections. So natural killer cells are not 100% effective, but they do a pretty good job at killing these cells that are either abnormal, have something wrong with their internal growth machinery, as in cancer, or are basically functioning like virus-making factories, which is what a virus-infected cell is doing. Now, they're able to act on the cancer and virus-infected cells before the adaptive immune system is activated. So that's why we're listing them under the innate, non-specific defense system. They're going to attack cells that lack self-cell surface receptors, and I'll just talk about that briefly. Most of the cells in your body that are supposed to be in your body contain a cell surface marker that says, hey, I'm supposed to be here. And if something happens to that cell, if it becomes cancerous or virus infected, that self-surface marker that says that cell is supposed to be there gets distorted. And if it gets distorted, it gives off a signal that says something's wrong with me. And it's that signal that natural killer cells recognize. They're able to kill these cells that are either cancerous or virus infected by a process called apoptosis or cell suicide. In order to induce apoptosis, they use a kind of two-step process wherein we use perforins, which are proteins that create a pore in the infected or cancerous cell, and granzymes, which are enzymes that get inserted into this pore, and essentially the enzymes go in the pore made by the perforins, and they're able to induce the process of apoptosis by acting inside this infected or cancerous cell. We do find that NK cells secrete potent chemicals and also enhance the inflammatory response. Next, we're going to look at inflammation. This will be a longer topic, and that's because this is the trademark of the second line of defense for the innate defense system. And this is essentially the tissue response to injury. Now, inflammation is triggered whenever body tissues are injured. And really the first part of inflammation is to sound a chemical alarm. And this chemical alarm begins when something happens to tissues. So they go hand in hand. This triggering of body tissues are injured, and then we immediately get the trigger for the rest of the process, which is a chemical alarm. Chemicals being released and causing things to happen. Now, injuries that are associated or have inflammation associated with them may be due to trauma or heat or irritating chemicals, or even infections by microorganisms. Oftentimes, inflammation is going to work at localized areas. It's going to respond to localized infections or localized areas of injury. There's plenty of benefits to inflammation because inflammation tends to actually prevent the spread of the damaging agents, whether they're pathogens or it's just damage to tissue. We're able to dispose of cell debris and pathogens by using phagocytes. We also will alert the adaptive immune system in case the innate system is not able to really control the infection at a particular injury site. We also see that inflammation sets the stage for repair by bringing all of the components needed for healing to the area that's infected or injured. There are 4 cardinal signs of acute inflammation. Be familiar with them. Be able to explain the 4 cardinal signs of acute inflammation. So we're going to do that. The 4 cardinal signs of acute inflammation are redness, heat, swelling, oftentimes called edema, and pain. So redness, heat, swelling, pain. So know those are the 4 signs of acute inflammation. Now, sometimes there's a 5th sign, which is impairment of function. Oftentimes this is due to the pain and the swelling. So let's talk about inflammation. Let's talk about why those are the 4 cardinal signs. Well, it all begins with our chemical release, this kind of chemical emergency signal, because that's what sets the stage for inflammation, this inflammatory chemical release, as well as vasodilation and increased vascular permeability, followed by phagocyte mobilization. So let's look at those in detail. So what sets the stage for inflammation is our chemical alarm, our chemical release. These are inflammatory chemicals, which makes sense, they're promoting inflammation. And these chemicals are released into extracellular fluid by injured tissues or even immune cells. An example of inflammatory chemical is histamine, which causes vasodilation. Histamine can be released by basophils or mast cells, and it's a key inflammatory chemical. Other inflammatory mediators besides histamine include things like kinins, prostaglandins. You'll see prostaglandin a lot if you study the immune system. Also, if you look into toxicology. Cytokines, that's another key chemical you'll see. Cytokines are generally immune chemicals, if we wanted to be really simple with it. And if a pathogen is involved, you might see complement proteins being released as an inflammatory mediator. But all of these cause vasodilation of local arterioles. So that's important. We're going to see our chemical alarm, which is the release of inflammatory chemicals. Things like histamine, kinins, prostaglandins, cytokines, complement, they get released, and they're going to cause vasodilation of local arterioles. That's going to increase blood flow to that tissue. It's going to increase blood flow into the capillary beds that serve that tissue. And then if we make all capillaries leaky, if we make those capillaries leakier than they usually are, we're going to see that fluid leaks out of these capillary beds near the tissue more than they normally would. Also, because we've increased blood flow to this area, we're more likely to have white blood cells like phagocytes arrive to the area, but also some of these inflammatory mediators act as kind of a bat signal to our phagocytes and actually attract them to the area. That process is called leukocytosis. The process of attracting white blood cells to the area of infection is leukocytosis. So here's just a table for the inflammatory chemicals. I do recommend giving it a look over, but we're going to go into more detail about some of these, especially complement. All right. Now, let's look at what's happening after our chemical alarm and how it's going to lead to our 4 cardinal signs of acute inflammation. Well, first we have our chemical alarm. We have chemicals like histamine released. This causes vasodilation, so we get increased blood flow to an area, especially the capillaries of that area. So that's hyperemia. The capillaries are going to become congested with blood. Well, that leads to redness because inside the red blood cells that we find in blood is hemoglobin, and hemoglobin contains a red pigment called heme. So there's the redness. That's one of our cardinal signs of inflammation. Well, a byproduct of a lot of chemical reactions is heat, and a lot of this heat is transferred to the blood. So wherever the blood goes, so does heat. So redness and heat are caused by vasodilation, which leads to hyperemia. Now, increased capillary permeability, also caused by that chemical alarm system, will cause an increase in the amount of exudate that's found in tissues. Exudate is fluid that contains clotting factors and antibodies that, when we increase the permeability of a capillary bed, is able to leak into tissues or the interstitial space. Because we have excess fluid or exudate leaking into the interstitial space and possibly going into tissues, this results in local swelling. It results in edema. Swelling is another cardinal sign of acute inflammation. The swelling also pushes on nerve endings. Some of these nerve endings may be nociceptors. Some of them may just be intolerant to this excess pressure. And so that swelling pushing on nerve endings can cause pain. So that's how our chemical alarm system, our release of these chemicals that cause vasodilation, increased vascular permeability, and eventually leukocytosis can lead to redness, heat, swelling, and pain, are 4 cardinal signs of acute inflammation. Pain may also result from the release of toxins from bacteria, but that's only if a pathogen is involved. We may see that prostaglandins and kinins have a small role in this pain development. And you may be wondering, why are these things happening if inflammation is good, or it serves a purpose, or it increases healing? Well, there are benefits to things like edema. A surge of fluid in tissue actually is able to sweep foreign material into the lymphatic vessels because that excess pressure pushes pressure on the mini valves of lymphatic capillaries, and we'll see increased, essentially, lymph formation. And we'll see that fluid then be able to be processed not only through the collecting vessels of the lymphatics, but eventually through lymph nodes, which are major filters for the immune system. We also know that edema delivers clotting proteins and complement to an area. And these clotting proteins and complement may able to begin the process of hemostasis and possibly marking pathogens for destruction via opsonization. Clotting factors form the fibrin mesh. They act as a scaffold for repair, and we know that that mesh is also able to isolate an injured area so that invaders cannot spread. So that localization is all possible as well because of these clotting proteins and complement at the area. Now, the thing we haven't talked about that also occurs because of our chemical alarm that has been pulled is phagocyte mobilization. Phagocyte mobilization is essentially leukocytosis. The leukocytosis will be followed by a couple of other steps. Phagocyte mobilization usually mobilizes neutrophils first, then macrophages. So neutrophils flood the area first, macrophages follow. And if inflammation is due to pathogens, complement will be activated. Complement helps link the innate and the adaptive systems together. So adaptive immunity elements generally arrive after complement has been activated, but there will be a delay. The first step of phagocyte mobilization is that leukocytosis, wherein the release of neutrophils from bone marrow in response to chemical from that chemical alarm is going to cause white blood cells to begin to travel to the site of infection, neutrophils first. Part of this mobilization includes the movement of white blood cells to the area of infection. When they get to the area of infection, they start to slow down because they start to stick to cell adhesion molecules that are located on the endothelial cells of capillaries in the inflamed area. So they're slowed down, or they start to kind of stick to the capillary walls at the areas where these cell adhesion molecules are, and the cell adhesion molecules are in the capillaries of inflamed tissue. Since they're slowing down, they're able to not only stick to the walls of that blood vessel, but they're able to then more easily flatten themselves out and move in between endothelial cells, which is called diapedesis. So the processes of phagocyte mobilization include leukocytosis, wherein chemicals call white blood cells to an area, neutrophils first, macrophages follow. We also will see that other cells can be called to the area of infection. We have margination, where essentially cellular Velcro holds on to things like neutrophils and macrophages when they get close to the area of infection. Then diapedesis, once we have adhered to these neutrophils or macrophages and they've slowed down and they're no longer in regular blood flow, they're able to squeeze through the endothelial cells that make up a capillary and move into the interstitial spaces and tissues. And that last process is diapedesis. Once we get a neutrophil or a macrophage in a tissue or in that interstitial space, it's just going to follow the chemicals. It's going to follow chemicals towards the site of infection. This process is called chemotaxis. So chemo for chemical, taxis for the movement that's performed. And we're just going to see that the trail of chemicals will get thicker where the inflammation and the infection is occurring. And that's what the neutrophils and macrophages follow. They follow a chemical trail. And so we see that these chemotactic agents promote positive chemotaxis. So that's where neutrophils go toward the injured area, not away. That would be negative if they went away. And then really as the attack continues, the monocytes will eventually arrive. We'll see the same process for that phagocyte mobilization. Not only were they triggered, but then they were able to stick to the capillary wall, and they went through the capillary wall via diapedesis. Then they perform positive chemotaxis. But it takes about 12 hours after leaving the bloodstream for monocytes to become macrophages. So since they're late arrivers and they have to change into macrophages, they are only able to replace the dying neutrophils, and they remain for cleanup after the neutrophils have already died out, and they remain for cleanup during the healing process and prior to epithelial repair. So here's an image you saw in Anatomy and Physiology 1, but not talked about in as much detail. What was left out was essentially phagocyte mobilization. What was talked about was the healing process, the use of endothelial kind of growth factors, the use of growth factors in tissues, the fact that the epidermis, made up of epithelial cells, is able to almost completely regenerate, whereas connective tissues may form fibrosis or fibrosed scar tissue. So if this looks familiar, that's why. But now we're talking about phagocyte mobilization. What brought all these healing components to the site of an infection or injury? And that would be the process of phagocyte mobilization, which was begun by the release of inflammatory chemicals. So that chemical alarm that is sounded when a pathogen is in a tissue or because of tissue injury, that is what sets the stage for inflammation. It not only includes vasodilation, it not only includes increased vascular permeability, but it also includes phagocyte mobilization, which is made up of the steps that we see here: leukocytosis, mobilizing white blood cells; margination, having those white blood cells cling to capillary walls; diapedesis, having those white blood cells squeeze through endothelial cells and move into tissues; and positive chemotaxis, wherein those white blood cells follow a chemical trail to the site of infection or tissue injury. Here in figure 20.4, we can see the events of acute inflammation all together. So we have our initial stimulus, which is tissue injury, which sounds the chemical alarm. We're going to see that there are leukocytosis-inducing factors, other inflammatory chemicals such as histamine and complement and prostaglandin and kinin, and this chemical alarm is going to set into play the steps that we associate with acute inflammation, which include arteriolar dilation, increased capillary permeability, the attraction of white blood cells or leukocytosis, which leads to margination, diapedesis, and eventually increased phagocytosis of pathogens once those white blood cells arrive at the site of injury or infection. But we also see that arteriolar dilation led to increased hyperemia, which led to heat and redness, two cardinal signs of inflammation, that the swelling, because of excess exudate that goes into the interstitial space, can cause pain when it puts pressure on nerve endings, and that swelling and pain are two more signs of acute inflammation. So over on this side, not only do we see the chemical alarm causing certain processes, but we see how it leads to the four cardinal signs of acute inflammation. So you need to know the four cardinal signs of acute inflammation, and you need to know how they are caused. But heat, redness, pain, and swelling are the 4 cardinal signs of acute inflammation. The heat will locally increase temperature, and that locally increased temperature will actually increase the metabolic rate of cells. This can actually help them heal faster. And then that sometimes 5th cardinal sign of acute inflammation is generally due to the pain and swelling associated with increased exudate formation. But ultimately, these physiological responses, these signs of inflammation, they're all going to lead to a final result, which is healing. That's why we need inflammation in diapedesis to bring those phagocytes to an area so that we can get rid of pathogens, we can get rid of cell debris. We can basically clear the area of debris and anything that causes disease. We also want to be able to have leaked clotting proteins in that exudate, be able to temporarily patch the scaffolding of the tissues, basically kind of form a scaffolding for repair, promote healing. So I definitely recommend looking at figure 20.4, the events of acute inflammation. If you don't understand something in this graph, make sure to go back in this part of your chapter and look at those processes and what leads to not only the 4 cardinal signs of acute inflammation, but phagocyte mobilization. We also just want to acknowledge some homeostatic imbalances. We mentioned pus. It's a creamy yellow mixture of dead neutrophils, but also tissue cells and living or dead pathogens. An abscess is a complication that is associated with healing, and it's when collagen fibers are being laid down, but they're not able to push this pus to the surface. They actually kind of wall off a sac of pus of either living or dead pathogens as well, and it might need to be surgically drained because it's very dangerous to open an abscess, especially if it's still in deeper tissues, because we may see the bacteria get into the blood, and that may cause septicemia. Some bacteria, such as tuberculosis bacilli, which we talked about before, we know are resistant to certain types of digestion by macrophages, especially if we're using those acidic lysosomal enzymes. So it's possible that they form tumor-like growths, kind of similar to an abscess, but it's only going to contain bacteria that are resistant to digestion. And a granuloma is an area that is a tumor-like growth that consists of that infectious microbe and usually infected macrophages. It's possibly surrounded by uninfected macrophages or some fibrous tissue, and even though the bacteria may remain inactive for really forever, if a person's immunity decreases and any of those microbes break free, they could cause a serious disease that could be deadly. Our next topic is going to be antimicrobial proteins, so make sure to watch that part. We're still looking again at the second line of defense, but we're leading up to that adaptive immune system.